Okay, so first of all, I would like to thank the organizer for giving me this opportunity to present my work. So, is it audible now? Okay, so thank you organizers for giving me this opportunity to present this work. And I'm going to talk about generalized TMDs, which is for the gluons and the Wigner distribution in the boost invariant longitudinal space. This particular work has been done in the collaboration with Sujit and Tanmay, which I think Tanmay has left. So this is the outline of my talk. So first I would like to introduce what uh, what do we mean by Wigner distribution and what do we mean by these generalized TMDs. And then I am going to introduce my model, which is light front rest quark model, and then the conventions and the kinematics which we have used for the calculation of GTMDs, and then the results for this gluon generalized TMDs. And finally, I would like to discuss this Wigner distribution in the boost invariant space, which we have obtained from this gluon generalized TMD. And finally, I would conclude my talk. Okay. So this is the popular picture which we have kept seeing in the slides, that Wigner distribution is the most generalized distribution. And from the Wigner distribution, we can find out this TMDs. A lot of talk has been on this. And also we can find out this impact parameter distribution. And from, if we integrate this TMDs or this impact parameter distribution in K space or BPUP space, we will simply find out the pattern distributions which are universals, process independent. Now, not only this TMDs and PDF, we can also find out this GPDs, which is, we can also find out GPDs from this Wigner distribution if we integrate over the K-PUB and take the Fourier transformation with respect to BPUB and delta. Okay. But the interesting thing is that all this distribution which has been defined, it is defined for this xi is equal to 0, which is skewness is equal to 0. And so you can see you have this GPD, you take skewness to be 0 and you get GPD for the 0 skewness, and from there you can get all those form factors. So the next question is what happens when we are taking this skewness to be non-zero. In that particular case, the momentum transfer to the target is non-zero in the longitudinal direction, and in this case we have another set of distribution which are the more general, and from these distribution we can simply find out what are the distribution. This, for example, this Wigner distribution, we can find it out by taking the Fourier transform of this GTMDs, we get H, and from H for the 0 skewness we get this Wigner distribution. Okay. So now for non-zero skewness, we have GTMD, which is a function of x, K-PUB, del-PUB, and this skewness xi. And if we take the Fourier transformation of such GTMDs, we get this Wigner distribution which is 6-dimensional. So earlier when we take skewness to be 0, the Wigner distribution which we obtained was 5-dimensional, and now the Wigner distribution is 6-dimensional. And this particular article, particular paper discussed this particular distribution for hadrons. Okay, so now let us talk about what do we mean by this Wigner distribution. So Wigner distribution is nothing new, but it is a very common topic in your usual quantum mechanics. If we want to find out the phase space formulation of quantum mechanics, we can use this Wigner distribution. We take the wave function at two different point in the space time, and we take psi star psi. You take the Fourier transformation, you will get this Wigner distribution, which is a function of space as well as momentum. Yeah. So this is a particular example of this Wigner distribution. You have phase space, and the distribution which is describing our system is the Wigner distribution. Now the significance of this Wigner distribution is that from the Wigner distribution you can get your probability density in momentum space as well as in position space. Plus you can also define various observables just as an average of your operator or the observable weighted over this Wigner distribution. Okay, so this is the basic of the quantum mechanics. Now let us move to this boost invariant longitudinal space. So in general, in this scattering process, we define this impact parameter space BPUP, which is generally conjugate to this delta PUP. And delta PUP is the momentum transferred to this target in the transverse direction. Now, now what can happen during this scattering, we can also have a situation where momentum transfer to the target is also along the longitudinal direction. In that particular case, we can define another position space variable which is conjugate to this delta plus, and this particular sigma, which we are calling it to be boost invariant longitudinal space, this is that particular sigma. And we want to find out this Wigner distribution in this particular impact parameter space, or we can say it to be longitudinal impact parameter space. And if you are more interested in this particular impact parameter state, you can simply refer to this particular article by Brodsky and others. And so we have calculated this Wigner distribution for the gluon in this boost invariant longitudinal space. For the quarks, we have already done, and the result got published. And this particular work, which is under communication, has been done for the case of gluons. Okay, so this is the gluon GTMDs. So we define these gluon GTMDs as a matrix element of the this generalized gluon correlator function. So just like PDFs or the GPDs, we can also parameterize this gluon correlator function in terms of various functions. And in this particular case, when you parameterize, you will see that this particular m delta sz, you can write it down in this particular combination, and where this sz is defined by this particular quantity. Cp is the parity coefficient of the gluon operator, and this particular m is the matrix in the Dirac space corresponding to the gluon operator. So if you are more interested in this, you can look at this particular reference. It has been given there in detail. So now, so we can parameterize this gluon correlator in terms of these various functions, and these various functions are actually this generalized transverse momentum dependent pattern distribution function. So in order to find out this thing, what we need to have the understanding of this particular thing. We have to find out this, and then we have this u bar and u, and by having various combination of the polarization, we can find out each of these generalized TMDs. Okay, so and we have done it for the case of light front gaze, where we take A plus to be 0, and in such situation, the gaze length, which is W and W prime. So in the case of gluon correlator, you have two Wilson line, and both of them reduce to 1. So we don't have to care about this. And also this gluon field strength tensor also reduces, because this A plus, these two terms becomes 0, and you have only this one. So we have to deal with only the transverse component AI. I goes from 1 to 2, and we can get the entire GTMDs. Okay. So for our calculation, we have considered this dressed quark model, where we take a quark which is dressed by another gluon. So this entire system we can think about as a spin half system, and then we can expand this state of this dressed quark in terms of one particle state or the two particle state. And then we can also use this momentum variable xi and qi to describe the particles. So in case of our calculation, we have restricted up to two particles. So this xi will be x1 and x2. So if for the quark we have x, so for the gluons it will be 1 minus x. Okay, so this is the kinematics which we have chosen. So for our initial target state, which is the dressed quark, this is the kinematics, and this is the final. So after the scattering, the target state for momentum is described by this particular thing, and the momentum transfer to this target state is given by this del, which is the difference of the initial and the final one. And since our stuck quark is the quark, the gluon of momentum, this x, which is the momentum fraction for the gluons, can be parameterized using this particular thing. Okay, so this is again the gluon correlators, which is the definition I have already shown. But what I would like to say that we can also write down this gluon correlator as an overlap of light front wave function. So these are the light front wave function which is associated with this two particle light front wave function, and using this we can easily calculate for the various combination what are these gluon correlators. So these are the results of our GTMDs where we considered unpolarized gluons, and in unpolarized dressed quark, these are the results of this GTMD which we have obtained. And also when we consider the longitudinally polarized gluons, in that case we get another set of GTMDs. These are the 4 GTMDs where this D and beta G we have defined in such a way. So these are the 8 GTMDs which we have obtained. So we have not considered this transverse polarizations. Okay, so one of the thing is that we have obtained this 8 GTMDs. So how can we be sure that these calculations are correct? So actually there is a very important property that these expressions should satisfy, and that is that when this xi goes to minus xi and this k goes to minus k pop, then there should be a change of sign overall. So it should be either plus or minus. So for our case, in our model, we obtained that our analytical expression for all this set of 6 GTMDs, it is plus, overall plus sign. And for these 2 GTMDs, we are getting an overall sign of minus. So in such a way, we can say that since this particular constraint is being satisfied, so there is a this calculation are error free. There is not inherent problem in this GTMDs expression. Okay, so now we have obtained this 8 GTMDs. Now we are going to calculate using these GTMDs various properties of the gluon. So the first thing that we can do using this GTMD is to look at what is the spin orbital angular momentum and the spin orbit correlation for the gluons in this particular dressed quark system. So if we integrate this one for the lower cutoff of 0 and upper cutoff Q of 50 GeV, what we have obtained is that this S has an overall negative sign. This orbital angular momentum also has a negative sign, but this correlation, spin orbit correlation, is positive. So from this particular thing, we can directly infer that the spin and orbital angular momentums is both are negative. They are aligned. Plus, since this is our spin orbit correlation is positive, we can say that the orbital angular momentum of gluon and spin of the target is anti-aligned. Okay, so now because we have this generalized TMDs, we can project it under some limit and we will get this TMDs. So these are the various TMDs which we have obtained using the different projections. So these are the relation which is model independent, and it is given in that reference of Lords and the others paper. So we can directly find it out, and we find that 2 of the TMDs are 0 in this particular model. Okay, so here we have plotted this TMD as a function of k-pop. We see that the magnitude are maximum near where for very low values of k-pop, for higher value of k-pop, it goes to 0 significantly. Okay, so now we have this something called helicity and worm gear density. So these two quantities or these two densities are defined in such a way using the various combination of your TMDs, and what we can so this particular thing we can interpret as this helicity density rho g as the probability density of gluon inside a target with a given momentum x and k pop when the target is longitudinally polarized. And here the probability density of circularly polarized gluon when the target is transversely polarized. And these are the plot in the momentum space. What we observe is a kind of cylindrical symmetry, and in this particular case we can see this is the worm gear density. The contours are uniformly distributed, but here the contours are not uniformly distributed. Okay, so using GTMDs we can also define something Wigner distribution which can be used to study the spin-spin correlation for a parton inside a given target. So what happens is that we can this particular rho lambda defines the Wigner distribution for a gluon with longitudinal polarization lambda in a strongly bound state with longitudinally polarization lambda. So all these various component LU, UL, LL, these corresponds to distortion which we see when suppose these things are not here, we will have the Wigner distribution of unpolarized gluon in unpolarized target. Now because of the presence of these various quantity, what we see is distortion. So the distribution should be get distorted in some way. So what we see is that, and what is interesting is that we can take this lambda and we can flip it. So here when this the polarization of gluon or the helicity of the gluon is in same direction with the helicity of this target, which is dressed quark. This is the distribution which we observed, which is of course distorted because of these distorted terms present. And when we simply flip the helicity, the entire distribution get shifted in longitudinal, in diagonal direction. So this kind of shifting has been observed in other model also, in scalar diquark model also, but that shift was only along this longitudinal direction. But in this particular case, what we are observing is that there is a shift, but along the diagonal directions. Okay, and even though there is a shift in the entire distribution in this impact parameter space, we do not observe any shift because of this helicity flip in your momentum space. In mixed space, we also see the distortion, and this distortion also, these are the dipoles, so distorted dipoles, and these dipoles are going away from each other when this helicity gets flipped. Okay, so now once we have all these things, we can now move to this Wigner distribution in sigma space. So here what we are doing is that we are taking a Fourier transform of this particular gluon-gluon correlator with respect to this parameter skewness chi. So when we take the Fourier transform, we get this particular thing, and then the upper limit xi max is restricted by the kinematics of the system, and using the various combination of this S and this gamma, we can define the this particular thing, which is the Wigner distribution of gluon in unpolarized or the longitudinally polarized target. So when we plot, so so this is of course the Fourier transform of this GTMDs, and this is again the Fourier transform of another GTMDs, these two Wigner distribution. And when we plot in impact parameter space, what we observe is that they show a diffraction-like pattern. So this is for Wigner distribution for unpolarized dressed quark, and also for longitudinally polarized dressed quark, we observe a similar kind of pattern. So that is a diffraction-like pattern. So now let me conclude my talk. So we have concluded, we have derived this analytical expression for gluon GTMDs in the dressed quark model for non-zero skewness, and this the leading twist to TMD in the model are also obtained because we can simply project this TMD as a generalized TMD as a special limit to get TMDs. Now this whatever the GTMDs we have derived, we used it to explore the gluon property in the dressed quark system, including the orbital angular momentum, spin orbit correlation, TMDs, helicity density, worm gear density, and what is the spin-spin correlation between gluon and this target state. And also we obtained this Wigner distribution in sigma space, which shows an oscillatory pattern akin to diffraction which we observed in single slit experiment. Thank you.
Thank you, Vikash. That is very nice talk. So questions?
Interesting, just one thing. So for xi not equal to x, 0, okay, you know there is also a particle number changing contribution in terms of light front wave function, right? There's 3 particle sector. If you consider a dressed quark set, there will be contribution from overlap of the 3 particle sector. In the reference of Brodsky et al., where I am also a co-author, we had considered both the sectors. So when you take a Fourier transform to go to the sigma space, actually you should consider both the contributions. So here you have considered the region where x is greater than xi, right?
Yes. Yes, yes.
Yeah, so what happened in our GPD calculation in that particular paper with Stan Brodsky was that, Dipankar may also remember, there was a singularity at x equal to xi, which got cancelled only when we took into account this particle number changing overlap. Did you also have a singularity at x equal to xi of the Wigner function?
Yes, I think we have.
How did you deal with it? You put a cutoff?
Yes, yes. So that's the cutoff here. This is the cutoff. This is the.
No, that is the cutoff on maximum xi that comes from kinematics. But when x equal to xi, in the GPD, there was a singularity which got cancelled when we took into account the particle number changing overlap. So just check later, you don't have to see immediately. Check later if you have this kind of thing. Otherwise, yeah, so maybe you can check the result a bit. But in that paper, we calculated the quark part. Dipankar, did we calculate the gluon part also? Yeah, quark part. Okay, so you may check your previous calculation. It would be interesting to also include that contribution, which you can include using the approach given in that paper. Okay, wave function is given in that paper.
Okay. Uh, so this is an integration over K-pub, right? So this is an integration over K-pub. So you have to take some lower limit and some upper limit.
I mean, is it model dependent things, or because if we integrate this K-pub, then we take from 0 to infinity, and here you
Ideally you should take it to be 0 to infinity,
Right,
but
right.
for practical purpose we have to limit it because there is an singularity if you will take infinity. So you have to take some upper cutoff, and the cutoff which we have taken is this 50 GeV, so that would be enough.
About while talking about the longitudinal moment, longitudinal position space, the Wigner distributions. So you have this integration of zeta max you just mentioned. So
Yes.
but it should
Yes.
also depend on x, right? Which x you are choosing, that will decide your integration limit, I think. But you have taken just all values of, I mean, zeta max is fixed.
This zeta max will be decided by what is the value of t, right? Because m is constant here.
Right,
so
but
m and minus of t. That is the two things that we have to choose. That will decide our zeta max.
But it should also depend on x, which values of x you are choosing. I mean, zeta max is the maximum for particular values of t. But while doing this integration, it should be zeta f, whether x is less than zeta max or x is greater than zeta max. It will decide your integration limit, I think.
So
Right, but the integration limit should be the minimum values of zeta max or x. If you take zeta mean is x. So what is the values of x you are choosing for your plot? Can you please?
it's I think 0.3. For these plot it's 0.3.
No. The longitudinal moment, longitudinal position space. Yeah.
Okay, here.
It should be. Yeah, it should depend on x, right?
Yes, I think we have chosen 0.3, Sujit. Yes.
Then what is the value of zeta max for different values of t? So is always less than x or is greater than x?
Less than x. So whatever you have saying,
that's
I
great.
understood. So we have done that. Right now, I don't recall those things, but
Okay,
I
that's
think
fine. I
we
just
have
want to
taken
know.
care of that. So you are saying that it should lie in within one limit.
Within limit. That's what I'm saying. Okay. Thank you.
Okay, so you said that these GTMDs, they satisfy some condition that if you replace xi by minus xi, it becomes either plus or minus. But that looks, so which one will be plus or which one will be minus? Is there any?
No, there is no.
Then if somebody gets minus in place of plus, how that both can be correct?
In this particular article by Low say and others, what they are saying is that this GTMD should satisfy this property, this particular thing. It should be either plus or minus. There should be an, whatever is there, it should be an overall change. Yeah, it cannot be both. It cannot be both. Yeah, so what we did is that, suppose this is the expression we have. Now we will change this k. Yes. Just give me just one second. हेलो, हाँ मैं आता हूँ, आप 2 मिनट वेट कीजिए. Yes, so yes, that's true. But what I am saying is, means if this is not satisfied, the GTMD's expression is not correct. So in that sense, we can consider that there is a little bit of certainty that the calculation, whatever we have done, is correct to some extent, not even 100%, but there is one 50-60% chance that this is correct.
Okay, any further questions?
Means we can consider it to other way. If this is not satisfied, the calculation is 100% wrong. So just the contrary.
Okay, I don't see any further questions. So thank you, Vikash, again.
Okay, thank you.
And thanks to all the speakers. And